Okay, good afternoon. Today we got to listen to Pere Rosselló. He's a master's student at the University of the Balearic Island, and he's working in the group of Banda Pascual in here in Medea, and he's going to talk to us about marine heat waves in the Mediterranean Sea.
Okay, thank you. So, indeed, I've been working on the Pascual physical operational oceanography group for 7 to 8 months now. I started with a high intro scholarship issued by CSIC when I did the work I'll present here today about marine heat waves, and now I changed. I'm employed by a graduate research contract issued by the University of Balearic Islands. I'll talk about a bit about marine heat waves, which is a topic that has gained increasing attention recently, and specifically, I'll talk about the results from an article that we sent 2 months ago, and that by now should be sitting still at some Frontiers Review folder, waiting to be read. And yeah, I mean, the presentation will be like half introduction, talking about a bit about global warming, satellite data products, and Earth system models and simulations, and then I'll talk how these things apply to the study of marine heat waves in the Mediterranean. So let's begin. The world is warming, and there is quite a bit of evidence that it is due to increasing greenhouse gas emissions by humankind, in case someone didn't know. And the thing is that although now climate emergency is everywhere in the soup, and at least for some people it's like the #1 priority that humanity has to address, we knew that the world was going to warm since 200 years ago or so. And this is quite interesting. There is this quote here from a woman climatologist, Eunice Foote, who kind of prophetically wrote in 1856 basically that increasing temperatures of CO2 would lead to global warming. No? And then a century went by and nobody paid attention to this. And it wasn't until the end of the 1980s in the US, during the Ronald Reagan administration, after a very warm summer, that the guy decided to create a kind of international assembly for climate-related issues. And then the UN stepped in, and the World Meteorological Organization stepped in, did their thing, and established the IPCC. And the IPCC is quite important. It's an intergovernmental panel on climate change, and they are responsible for the highest quality research on climate issues and climate change, both from a hardcore science perspective and policymaking perspective. And as the media coverage of climate is usually purely communicated, here a few peer-reviewed facts about the current state of climate. First, that the global surface temperature has increased faster recently than at any period since the beginning of the Common Era. This is from IPCC. Then from the European State of Climate report, that the Europe surface temperature is warming at twice the rate the global average. And then from our friends at SOCIET, there's an article which basically says that the Mediterranean is warming at a bit less than half a degree a decade. And then also from the IPCC, that the global surface temperature will continue to rise at least till the middle of the 21st century. So it's clear that we live in climatically exceptional times, but we live in exceptional times in many other ways. And one of them is because today we live in an era where there is a constant widespread coverage of satellites monitoring the Earth and retrieving all kinds of climate-related variables. And this thing began in 1956 with a little weather station, the Soviet Sputnik. And since then, there have been a never-improving and increasing number of satellites orbiting the Earth. And by now, in 2022, I checked, and there are a bit less than 5,000 satellites currently operational, and of course, for different purposes, and not all of them at service of operational oceanographers. But among those, there are a few of them that have a that are equipped with a thing called, how is it called, advanced very high resolution radiometer, which is basically an apparatus on a satellite that points at Earth and passively retrieves thermal radiation from the very top layer of the water column, which is called subskin layer and is less than a millimeter in thickness. And doing that, then they can infer the temperature of the sea, and you retrieve sea surface temperature, or SST for short. The thing about these measurements is that they are made in the infrared band spectrum. And one thing about this is that clouds are actually opaque to that spectrum of the electromagnetic radiation. So if it's cloudy, you have no data. And another thing is that most of the measurements that are used are actually taken at night, because at night you don't have diurnal fluctuations of temperature of this very top thin layer of water. And then at night, the temperature is actually representative of the 10-meter water column below. So this is the data that I've used for satellite data analysis. And the important thing also about this is that we have SST, sea surface temperature data, since the beginning of the 80s, daily data, and this is more than 40 years. And as this seminar is about extreme events, I want to stress one thing, which is having 40 years of data is essential to defining a normal baseline state of the oceans, temperature-wise, in this case, because only if you know what the normal state of the ocean is, you can use that as a benchmark for comparison of current events and say if some event that happened yesterday was usual, unusual, or extreme. No, because you can only say that something is unusual if you have enough data to actually know what usual means. No? So we have it, so we can do it. And this is okay for many years of, for example, I don't know what happened now, sorry. Okay, for example, with this data, you can start to plot some results. And this is, for example, the difference in temperature in the Mediterranean between the 80s and the last decade. And you can see that there is an anomaly that even reaches 2 degrees in the Adriatic and the Ionian Sea, on the Levantine Sea. And you can see a very well-defined warming trend here in your bottom left. Okay, so we have all the satellite data, but we are also interested in what kind of planet and oceans are ahead of us. And to do that, we have to rely on models, on Earth system models, which are pretty complex, let's say, simulations about Earth climate that predict like future projections of all kinds of climate variables like evapotranspiration, precipitation, sea surface temperature, atmospheric temperature, and so on and so forth. And as doing this thing requires enormous computational effort, what's actually done is that a few expert modeling groups around the world can cooperate, create these models, make the data available for everyone, and you can play with it if you want. And these models, I mean, they, since 20 years ago or so, they are kind of monopolized by an organization called CIMIP here, which kind of coordinates all modeling groups around the world, and those are the ones that set the basis for the IPCC reports that I talked just a moment ago, which are the gold and the standard for climate research. And the main question they seek to answer is, how does the Earth system respond to anthropogenic forcing? And we more or less know the answer. It's warming, and it's usually represented in these different shades of red palettes. And also one characteristic of these models is that for each model, there are different scenarios. Okay, for each model, for each modeling group, there are different scenarios called experiments, and also called shared socioeconomic pathways, which are basically assumptions of how humans will behave in the future. like regarding economic growth and prosperity and basically emissions of greenhouse gases and so on and so forth. And I'll do what most people do in this case, which is to take the two most extreme pathways. Okay, one thing that I wanted to say, which is that the models do not predict human behavior; they assume human behavior and then simulate Earth response to that. And here, for example, you have greenhouse gas emissions for different scenarios. No, and there is the green pathway, the most optimistic one, like ecological wonderland. We will go net zero by 2080. And then there is the other extreme pathway, which is called business as usual, which means no regulation of greenhouse gas emissions, no carbon tax, and we burn coal, and so on and so forth. And I will take these two extremes. And in reality, probably humankind will lie somewhere in the middle because we're already off track of the green pathway, and it's difficult to imagine a future with no renewables at all. So another thing about models is that they are not perfect, obviously, because they are models, and they have their inaccuracies and problems with resolution and so on. And there is this famous quote from a statistician, George Box, who said, "All models are wrong, but some of them are useful." And with CMIP models, is more or less like this. I mean, and the methodology is to grab maybe 25 models, which may have their inaccuracies, average them all, and then you hope that the mean value is something resembling reality, which does quite a nice job because, for example, here you can use these models. Hold on, I don't know what's happening. To actually plot the projection of sea surface temperature in the Mediterranean. And what we see here, the filling regions are all the model results, like 22 of them, since the 1800s to 2100. And in gray, you have historic simulations till 2014, and then in green, you have the green pathway, and in red, you have the coal burning pathway. And then in blue, you have the satellite data for SST in the Mediterranean Sea. And first thing you see is that the results match pretty well. And the other main takeaway is that indeed, at least the Mediterranean Sea, with most probability will continue to warm at least till the mid-century. Okay, and one thing that we can think about when looking at this is, okay, mean SST is increasing, then this will mean that extremely warm temperature events will be more common, and those are called burning heat waves, and we can talk about them now. And they are defined analogously with respect to atmospheric heat waves. They were defined a little bit later, and there is not that much research. The first definition came in 2016 by a paper from a paper by Hobday et al. And basically, they define them as prolonged, anomalously warm water events that take place at a specific location. And prolonged here just means that they must last at least 5 days. And anomalously warm means that SST, surface temperature, should be above a predefined threshold. And then what kind of threshold? Well, it has to be different for summer and winter, because then you won't detect winter marine heat waves. And to define it, the procedure is basically to choose a baseline climatological period, for example, from 1982 to 2002. Then for each calendar day, you get an SST distribution, and you take the 90th percentile of that. That is, you take the unusually warm temperatures from a given day, from a given baseline period, to actually set the threshold. And this is way easier to see in a plot than to actually explain it in words. So you have it, for example, here, and this is the SST time series for a point in the Balearic Sea for this summer, for this year. And data is still November till yesterday or past yesterday. And in red, you have the threshold, and in black, you have SST, and filled in orange, you have the days where there actually was a heat wave. And you can see here the heat map for the temperature, which reached even 30 degrees in some regions. And I think, I mean, here there are some, I don't know what happened to this Earth. It doesn't have continents. I don't know what happened. Those are some main marine heat wave events. I won't talk a bit too much about this, but for example, there is a 2003 marine heat wave in the Mediterranean Sea, which was related to mass mortality of benthic organisms and so on and so forth. And also in Australia, which is somewhere around here, I suppose, is related to the bleaching of coral reefs and so on. And then the thing that should worry us, or at least worried me, about marine heat waves, which is its definition. The current consensus is to set the baseline period from 1992 to 2001 or 2012 or something like 20, 30 years. Okay, and for example, in the Mediterranean Sea and most of the oceans, we know that the mean temperature is increasing. So, for example, let's take these figures and let's assume that this is the SST distribution for a given day. Okay, then you would have the 90th percentile somewhere around here, and you set the threshold, and temperature falling here would be marine heat waves. But then you have warming, so the mean is shifting, which means more marine heat waves. How many? Well, it depends on how much it warms, but it can be maybe a quarter of a year or half a year or something like that. And those are lots of extreme events. And the question is, are they extreme events? And this is more or less the crux of the biscuit. And to answer it, we can look at data for the Mediterranean Sea. And what we are looking here at is mean marine heat wave days in the Mediterranean Sea using this fixed baseline period for threshold delineation. And we can see that there is a spike in 2003 and that it is increasing despite some variability. And when I came first here at IMEDEA, what I was told is, okay, make a project, predict how this thing will evolve in the future, maybe with machine learning or something like that. But the thing is that if you actually take the hot day definition of marine heat wave with fixed threshold, you know where this thing is going, because you have warming temperatures and you have fixed that will surpass fixed outdated threshold from the 80s. And more or less, you can imagine that something like this will happen, that eventually in the Mediterranean Sea, we will reach a permanent marine heat wave state. No, this is basically what it is. And this I drew myself, but if you actually put model data and you calculate marine heat waves for these CMIP models that I was talking about, you find exactly the same thing. Those are simulations for 22 different models for the red pathway and the green pathway. And you basically see that the marine heat wave is reaching a permanent, the Mediterranean, sorry, is reaching a constant marine heat wave state. No? And this would be good for, would make some good headlines, and it has done, but it should worry us a bit, or at least fill us with a bit of semantical unease, because they are called marine heat waves, but a wave formally is defined like periodic or episodic disturbance of some medium with respect to its rest state. No? So this is not a periodic or episodic disturbance. And actually here an analogy with sea level rise may be useful, because if you have a beach and you have 1 meter waves, then if sea level rises for 2 meters, you won't say that there are 3 meter waves. You would say that there are 1 meter waves on top of 1 meter level rise. No? And those are actually also called extreme events. And if you go to the definition of extreme event, no, thank you for listening. No, I don't know. You go to the definition of extreme events, you have something like not usual or exceptional. Again, something that happens every day of the year with some trouble will be exceptional, and very severe or serious. And this is maybe more acceptable, the definition, but you have to answer severe with respect to what and serious affecting whom. Well, because when it comes to the impact of marine heat waves, it definitely causes mass mortality for some organisms, and some organisms will migrate, and some organisms will actually thrive in increasing SST. And what's the way around this? So it's been reported in the literature, although it's not been endorsed by many people, is to actually move the baseline to, yeah, I don't know, for example, if you want to calculate when heat waves for 2022, you use a baseline climatological period of the 20 years prior to that. And you do that, and you can get different results, which kind of make assure that these events will be rare. So you can call them extreme, and they'll be shorter, and they won't saturate. Those are the results from the Mediterranean Sea for satellite data and model data using a 20-year moving baseline. And also, only if you do this, you can extract statistics, because if you have saturation, all the statistics are messed up. And I mean, I don't want to talk about this either, but we can look at it later. You're going to set the statistics for number of magnitude waves per year, their intensity, the duration of the events, cumulative intensity, and so on and so forth. And summing things up, and this is the end. Okay, so I basically talk about these possible two definitions. There's actually a third one, which doesn't really fall into the category of heat wave, but it's sometimes used, which is absolute thresholds, which are useful for biological applications, because some species, if some temperature is surpassed, die or something like that. And this, for example, these three figures are data for SST 2022 for a point in Balearic Sea. And this threshold, for example, is the 28 degrees that in theory is the critical temperature for Posidonia, which was surpassed for almost a month this summer. Well, and then for moving baseline and fixing the baseline, and some concluding remarks is that it's actually a matter of time scale. Right? If you want to make a statement about the fact that the temperature of the Mediterranean Sea has warmed with respect to the 80s, you could use a fixed baseline and say that there is a permanent heat wave state or something like that. But I would say that this is stretching the meaning a bit too much. And instead, if you use a moving baseline, then you keep heat waves rare, extreme, unusual events. Then, therefore, you can link to other unusual events that may fall, and then you can retrieve the statistics with that. And the whole point is that in order, when you create an indicator, at least I would say, a marine indicator, I mean, one has to be able to use it for decades long, no? And this is the reason I would at least consider using this moving baseline, which is currently not done in the literature when talking about these issues. At least consider it. And well, this is it. Thank you for listening. And if there are any questions, I'll be happy to answer if I can. Because usually this raises some debate. Sure.
So I have two questions. Actually, I'll ask you the second one, which is not actually immediately related to this.
Okay.
So I'm not an oceanographer. So the fact that it's, if I understand well, what you have is that you are warming very fast the top layer of the ocean. Right?
Yeah.
So that would seem to mean to me that you increase the temperature difference between the bottom and the top of the ocean. What sort of consequences is this going to have, or is this going to have any consequence?
Okay, I'm a novice oceanographer. I actually, but I mean, I've read that marine heat waves are linked to the stratification of the upper layer of the ocean, and if I'm not wrong, this may have some issues regarding mixing between the layers. But like around there.
Well, I was more thinking about the fact that maybe if you have less mixing, then actually this increases even more the rate of warming up of the top layer.
Yeah, it's entirely possible. And the other question?
No, the other question was that maybe I didn't really understand the last bit with the moving threshold. Because it seems to me what you have is you have a distribution of temperatures.
Yes.
And then what you're saying is that if the distribution shifts and I keep the threshold fixed at a certain point, the whole distribution is going to be beyond the threshold, and this classification is completely useless because it doesn't actually tell you anything about what goes on in terms of temperature fluctuation. Okay. And that's fine. And I think if I understand well, your alternative is essentially to look at always the tail of the distribution, meaning.
Yeah, basically instead of defining the threshold with the distribution, let's say that goes from 1980s to 2000, like said in the past, you actually set the threshold with the distribution of 10 from the 20 years.
Right, but okay.
And then it updates.
And this goes in the direction of my question. So that it means to me that that might be two different alternatives. One is the shape of the distribution stays the same.
Yeah.
And then what you're doing essentially is you are shifting the threshold together with the distribution, and then you get, let's say, you get a flat distribution of outcomes, which is essentially what you saw.
Yes.
And you haven't learned anything really from this, it seems to me, except that the shape of the distribution stays the same. But the alternative is that the shape of the distribution changes.
Yes.
And then you're still going to have a dynamics that will tell you something. But then at this point, wouldn't it be better to just look at the distribution as opposed to looking at arbitrary thresholds? So just plot the distribution in blocks and you see how this distribution changes.
Yeah, but usually with these things, especially when you create indicators, you want to like an easy number for people to actually talk about.
Right.
And because people love to talk about money heat waves, because you can say that there is a money heat wave, which means that things are warmer than usual. But then you go into all the nuances of the definition and you get all confused, which is what happens in this field. And yeah, I mean, obviously looking at the distribution is the best choice, because then you know what's actually happening. If actually it's not shifting in temperature, but maybe spreading, and it would mean more variability, more extreme events as well. And there is an article which looks at which is the main driver of magnetic heat waves in the whole in the oceans, all the oceans, and almost all of them are driven by warming. Like increase in variability, it seems that it's not a big deal. But the whole point here, for example, moving the threshold, is that you have the indicator that whenever it happens, because what interests you here is to say, okay, first week of August till third week of August, there was an anomalously warm period. I mean, you want to be able to make a statement like that. And in order to make a statement like that, which means this information, anytime, this decade or the next decade, you have to do it with a moving threshold. Because if you use a fixed threshold, all year will be, or half a year will be anomalously warm. No?
I don't quite see the point. I think there's an underlying thing about what actually we want to define a heat wave. And at the end is something that it actually is a departure from a trend. So I will start to the trend in the series, which the entire series, you don't have to go by 3 years or 3 years. You just look at the under to low frequencies, let's say lower than decadal frequencies. You remove that, and then you have the variability, which is super decadal, the variability in which you can actually then analyze the episodes that you have there. And I think that you can do a good job there, just defining those episodes are longer in time, they are higher intensity, etc. That you always work with departures. Then when I say that, I don't understand what's the point of giving an exact value. I mean, I would say just relatively to the actual trend, how much am I above or below that certain level, which is actually what most organisms, and if you want to put it on that side, is they are going to suffer. Most of the organisms respond to higher frequency variability, not long trend departures. So I think that the interest is over there, and I would just simply retrain all those services.
Yeah, okay, so that's a very good point, and it's actually an option. Just to retrain the series, look at the variability, and also remove seasonal variability, and you simply look at departures from this series. But the problem is that there are many modes of different frequencies regulating this time series. And if you do that, you also have the problem that you cannot compare marine heat waves in different places of the planet. Because for example, in South East Pacific, where El Nino happens, you would have much more. I mean, you cannot apply the same criteria. You may have some trouble applying the same criteria for the trending there, with very pronounced decadal variability that may be in the Mediterranean. The criteria for the trending. So it's kind of, I'll say that it's a bit less universal, and with moving the threshold, we are actually detrending at the end of the day. And by choosing the length of the baseline period, you are removing, let's say, higher frequency variation. Because if you have a 40-year moving baseline, then you will remove decadal.
Yeah, but it's just to mean you are assuming it's linear, but it doesn't have to be linear itself.
No, it doesn't necessarily have to be linear. But if you move the threshold and the temperature drops, then you. But there are many options, and I thought about actually trending because it may be a better idea. I'm not certain that this is the best idea. What I just want to say is that at least the main message is that whenever one hears about this marine heat waves, like for now, everyone assumes it's a fix. Most people do their calculations and publish the result with a fixed baseline, and you get all this saturation and extreme events and all the year round and all this stuff. And it just maybe if it has served for just knowing that there is a nuance there in the baseline definition that actually people are starting to question and to play with, then that's enough for me. And there may be better options. But
yeah, in this respect, trying to follow the conversation, it seems to me that you are actually interested in the tail of the distribution, right?
Yeah.
And then to give a number, you have to decide on either on filtering or depending as I also said, or this 20-year period that you have to decide whether it's 20 or 25 or 30. But then I think you're missing something important. And partially you say that if you depend or if you do this kind of analysis, then different sites are not comparable because they have different variability, right? But you can actually capture variability. You are using here a stationary analysis, right? I mean, you are assuming that during the period that you are analyzing, your distribution of these extreme events is not changing, but it might be changing. And you can introduce that. You can actually give a metric, which is quantitative, talking about the number of degrees, which is what you want, I assume, right? But this can be time varying, and this can be time varying different in different places. You can introduce ENSO variability as one of the potential processes affecting the variability, or NLO, or whatever. If you introduce the non-stationarity in your estimate. I mean, there are some other tools, some other ways that I think are more suitable for this kind of analysis, instead of fixing a period or threshold or whatever.
But I think I didn't fully get it. I mean, here the issue is that you either include the one. I mean, we're in a scenario, for example, in the Mediterranean, which is the case I studied. Basically, you have a very pronounced warming trend, and you have to make the decision of including this warming trend in the definition of an indicator that it's supposed to detect extreme events, or you do not include it. And my argument is marine heat waves are defined by the IPCC and the World Meteorological Organization as extreme events. So in order to have a definition that keeps these events rare, which maybe it's not a very useful definition. I actually do not say that non-heat waves can be used for everything. It's just that solving a bit this indicator if people want to use it.
I can tell you how we deal with this kind of problem on
Yeah,
the policy level, because we also have extreme events and we define the tensors, and then we apply on a stationary analysis over subsample space. In that case, you don't have to assume any shape of the original, of the complete distribution. It's not necessarily Gaussian, and changes can be in the variability, and changes can be in the mean, and this is implicit in your assumptions, right?
Yeah, but here as well, I do not make any assumption about the shape of the distribution.
Well, yes, you remove the mean because you are shifting.
Well, only that, yeah. Yeah.
Well, and you are looking at the entire distribution, but you're interested in the tail of the distribution.
Yes.
What I'm saying is that it is much easier if you just model the tail of the distribution and you don't make any assumptions about the whole distribution. It doesn't really matter how the whole distribution changes. If you are able to model the tail of the distribution. Because the tail always fits within extreme distribution.
Yeah, but
irrespective of how the entire distribution is.
Okay, and where do maybe I've missed it, but where do you get the distribution from?
Well, when you are talking about extremes, all distribution converts to the same families of distribution of extremes, generalized or Pareto or whatever.
Okay. So
you can model that and forget about the entire distribution and forget about the trends, because everything, all the information will be there. And then you can model that with variability, time variability, or without time variability.
I'm interested in that. I'll ask you later.
I agree that maybe this is the correct way to proceed, but the thing is that we are trying to do something much simpler and still difficult to convince the community of people who are working on integration. We should go step by step.
Yeah, exactly.
Working on my integration also interested in this topic are not at the same stage of the CO2. So maybe
It's another variable, it's the same.
with the conversation, we have been working on this, and there were having some discussions with also marine biology, and so I think we need to, I think we need to go.
It has to be understandable.
I don't think this is wrong. I mean, I just say that what you want to do, there are ways to do. Exactly. So there are methodologies that are developed to.
Yeah, for sure. I may not know it. Yeah, but the thing is that the current state of discussion about these topics, I mean, I was discussing it at one workshop, and it was they actually brought the point that moving the baseline is bad because you don't send a political message about warming. I was like, like I didn't know that sending a political message was the aim of doing this kind of research, instead of actually trying to create an indicator that works. No? There may be ways for it to work better, but yeah, that's the stage of the discussion, more or less.
Sorry. The temporal trend seems quite easy to understand. Increasing, so to move like the Galileo problems. If you work on a boat that is moving, what is your speed? But what about the spatial distribution? I mean, do you expect that the heat wave will still occur in the same places, or as some people here say, maybe some places are warming more faster than other, or
Yes, here there are, I mean, once I decided I was using the moving baseline, there are a few things that follow, which is if region is warming faster, because the distribution has to keep up with the warming temperatures, you will actually detect more magnitude waves. So there's actually let's say one could say a coefficient of the amount of magnitude wave days that depends on the trend. So the greater the trend, the greater the magnitude waves, and also the greater the variability. If the variability of the distribution is changing, you will also have trends in magnitude, increasing trend. So it's actually not perfectly flat, and And using this analysis, you can also infer regional differences among regions of the ocean that have different.
Yeah, but do you expect the difference you're finding now are also the same that you will find with another threshold in the future? Or there can be kind of one region is not showing any more
I mean, the thing is that if the distribution of one grid point, let's say satellite grid point, changes in time, which some way or the other all do, then you will have an unequal wave because some points will fall outside the. Well, if it doesn't change, because the definition is with the 90th percentile, then you will have 10% of unequal wave. If the and some may say that this is too much, because the 90th percentile criteria is actually used for in atmospheric science for defining warm nights. So not extreme, they are just warm, and here we use it for extreme events. But some may argue that it's a bit too little to use 90th percentile. But yeah, the thing is that if the distribution doesn't change, you will get 10% of unequal wave. And if it changes, like stretching towards the tails, you will get more. If it shrinks, you will get less. And this depends on the region. Yeah.
Just a curiosity, because it looks like the southern Mediterranean is quite different in behavior from the northern Mediterranean. Is that linked to anything? Like currents? Are they usually the southern Mediterranean more colder? Or?
I mean, what I can say is that, which links to what we were talking about, that around these regions we have higher variability. And higher variability, we expect higher variability to lead to more magnetic waves. For example, here you have a cumulative intensity, which then this result makes sense by looking at the variability of the SST time series around the Mediterranean. Those regions around here have higher variability.
Is that due to wind?
I have no idea.
Because I was thinking there is the border
very related to India. You have Mistral, you have
close to Trieste, there is the border.
yeah.
Yeah,
And in Greece, you have it's probably in Greece, Nantemi. And that looks very similar to a wind distribution. The cumulative.
And here, for example, the number of magnetic wave days, this figure resembles a lot the actual plot of trends in the Mediterranean. Because I mean, you have the Levantine Sea that is forming faster than the west side, and you actually have this anomaly here, which is the Yera-Petra gyre around Crete, which is not warming, and you see that perfectly with magnetic wave announcement. Okay.
I think simply that this approach, like intermediate between having the fixed threshold, when you take the full effect of the global warming, the entire intended baseline, where you remove all these effects. I think in that one, you still have some effect of global trend, with global warming, like less than the fixed, but more than the different.
Yes.
Maybe the question is that what do we want in the night wave definition?
Yes, exactly. That's the question, and that's the question.
Or do we have maybe two definitions in night wave?
Yeah.
One with and one without. Only the processes or the processes.
Usually, what will happen? I mean, it doesn't seem like a very big deal, to be honest. But it's also an issue that doesn't have a universal solution, because the universal solution is everyone agreeing on the same definition and using it, which can more or less happen with the fixed baseline and so on. But at the end of the day, what happens is that there is a paper on magnetic waves. They will spend one paragraph or two explaining what definition are they actually using, and then with that you can interpret the results they're obtaining. But the thing is that when this goes from scientific literature to the media, obviously everything gets mixed up, and magnetic wave happens every day, and everything is extreme, and so on.
Maybe you should propose a definition in the paper.
But I mean, and the article is basically because the thing is that there were papers studying the trends and the statistics of foreign heat waves in the Mediterranean using fixed baseline, but there weren't any using moving baseline. So it's like, okay, you can do it this way. Here you have it. If you're interested, you take it.
Thank you.